Space. We call it the final frontier, an endless, silent ocean of stars, holding breathtaking beauty and unimaginable scale. But this beauty hides an environment of absolute hostility, utterly alien to human life. It's a vacuum, radiation-soaked, with temperature extremes that defy earthly comparison, yet driven by an insatiable curiosity, we venture into it. For astronauts, this void is a workplace, demanding peak physical condition, immense courage, constant vigilance, and an unwavering trust in the complex web of technology that shields them. At the heart of this protection lies the spacesuit, a personal spacecraft, a miracle of engineering designed to provide air, pressure, and protection against the lethal emptiness just inches away. But technology, no matter how advanced, carries inherent risks. What happens if that vital lifeline, the spacesuit, fails? Imagine the scenario. A micrometeoroid impact, a material defect, a catastrophic tear. What if an astronaut's helmet, their window to the cosmos, cracks open in the silent void? What unfolds in those first, disorienting, terrifying seconds? Does the human body instantly explode, a gruesome spectacle ripped from the pages of lurid science fiction? Do they flash freeze into a brittle statue in the supposed absolute zero of space? Or, against all odds, could there be a fleeting chance of survival? The truth, grounded in physics and grim physiology, is perhaps stranger and more chilling than any fictional portrayal. Popular culture, especially movies, has often painted a dramatic and frankly inaccurate picture of death in space. The most common trope? The instantaneous explosive decompression, a human body violently bursting apart. Let's shatter myth number 1. You do not explode. The vacuum outside creates an extreme pressure difference compared to the pressure inside your body. Tissue possess remarkable tensile strength. They are strong enough to contain your internal pressure. You wouldn't rupture like an overfilled balloon. What would happen is significant swelling, a condition called edema, as gases trapped under the skin and in soft tissues expand dramatically. It would be grotesque, but not explosive. Now for myth number 2, your blood boils. This holds a grain of truth, but it's often misunderstood. The near total absence of pressure in space drastically lowers the boiling point of liquids. This phenomenon, known as ebullism, would immediately affect the exposed liquids on the surface of your body, your eyes, the lining of your lungs. These would rapidly vaporize, effectively boiling away at your normal body temperature. Imagine the bizarre and painful sensation of your saliva bubbling. This rapid vaporization also steals heat, causing intense localized cooling on these surfaces. But what about the blood coursing within your veins and arteries? Your circulatory system maintains its own internal pressure. This pressure is high enough to prevent your blood from spontaneously boiling inside your vessels. And myth number 3, you freeze instantly solid. Space can be incredibly cold, plunging to hundreds of degrees below 0 Celsius in shadow, while surfaces in direct sunlight can bake at over 100 degrees Celsius. But the vacuum itself is the key factor here. It's an almost perfect insulator. Heat transfer primarily occurs through conduction, convection, and radiation. In the vacuum, conduction and convection are negligible. Heat loss happens mainly through radiation, which is a surprisingly slow process for a human body. You would eventually freeze, yes, but it would take hours, long after other lethal effects took hold. You wouldn't become an ice statue in seconds. So, what is the real, immediate, and inescapable killer in the vacuum? Asphyxiation. Lack of oxygen. The vacuum doesn't just mean there's no air to breathe. The extreme pressure difference actively and violently pulls the air out of your lungs. If you tried to hold your breath, the pressure differential would fatally rupture your delicate lung tissue. The only reflex would be to exhale forcefully. Within moments, the oxygen in your bloodstream plummets. Your brain, starved of its vital fuel, would shut down. Unconsciousness arrives swiftly, likely in 15 seconds or less. That brief window of terrifying awareness is all you'd get. This isn't merely theoretical speculation. History holds a stark example. In December 1966, during the height of the space race, when NASA was pushing the boundaries of technology for the Apollo moon landings, a spacesuit technician named Jim LeBlanc inadvertently became a human test subject for vacuum exposure. He was inside a vast, multi-story vacuum chamber at the Johnson Space Center in Houston, testing an early prototype of the Apollo spacesuit, the very type meant to walk on the moon. These tests were crucial for ensuring astronaut safety in the harsh lunar environment. Suddenly, during the test sequence, the vital hose supplying pressurized air and coolant to LeBlanc's suit became disconnected. Within seconds, the suit's internal pressure crashed, dropping from a stable, life-sustaining 3.8 pounds per square inch down to almost 0, effectively exposing him to a near-perfect vacuum inside the chamber. LeBlanc later recounted the horrifying final sensation just before his world went black. His own words paint a chilling picture. As I stumbled backwards, I could feel the saliva on my tongue starting to bubble, starting to boil. And that's the last thing I remember. The embolism he described was real. He lost consciousness within approximately 14 seconds, succumbing to hypoxia. Outside the chamber's thick viewing ports, his colleagues, including Supervisor Cliff Hess and fellow technician R.L. Clay, witnessed the suit deflate and LeBlanc slump over. Their reaction was instantaneous. Understanding the lethality of the situation, they initiated an emergency repressurization. Normally, bringing the massive chamber back to atmospheric pressure was a slow, careful process taking up to 30 minutes to avoid structural damage. This time, safety protocols were overridden. Air was blasted back into the chamber at maximum speed. Incredibly, they managed to restore breathable pressure in under 90 seconds. Some reports suggest initial, life-saving pressure returned even faster. Inside the suit, LeBlanc began to stir as oxygen reached his brain again. He regained consciousness. Astonishingly, after medical checks, his only reported injury was a persistent earache from the rapid pressure changes. He had stared into the void and survived, a testament to the body's brief resilience, but more importantly, to the critical importance of immediate rescue and repressurization. His experience provided invaluable, albeit terrifying, data for spacesuit design and emergency procedures. So, let's meticulously break down the physiological cascade that occurs when a human body is suddenly exposed to the vacuum of space. Second, by horrifying seconds 0 to 2, explosive decompression. The first violent event is the air being forced from your lungs. Any attempt to hold your breath against this pressure differential would cause fatal barotrauma, ruptured lungs. Instinct or training would demand immediate exhalation. Seconds 2 to 15, acute hypoxia and loss of consciousness. With the air gone, oxygen transfer to the blood stops. The oxygen already circulating is rapidly consumed by the brain. You remain conscious, aware of your catastrophic situation, for a terrifyingly brief window, estimated between 9 and 15 seconds. Then, mercifully perhaps, unconsciousness occurs as the brain shuts down from oxygen starvation. Seconds 15 to 30, embolism and edema commence. While unconscious, the surface effects begin. Water on the tongue, in the eyes, and lining the airways starts to vaporize due to the low pressure, causing localized cooling. Simultaneously, the lack of external pressure allows gases dissolved in body tissues to expand, leading to noticeable swelling, particularly in skin and extremities. The body visibly puffs up. Seconds 30 to 60, circulatory system impacts. The cardiovascular system struggles. While the heart may continue to beat weakly for a time, the formation of water vapor bubbles in the venous blood can create blockages, severely impeding circulation. Oxygen delivery to tissues effectively ceases. The swelling becomes more pronounced. Seconds 60 to 90, cardiovascular collapse and death. Without oxygen and with circulation failing, irreversible damage occurs. The heart stops. Brain death follows swiftly. Experts estimate the absolute maximum window for survival, assuming immediate rescue and repressurization within this time frame, is around 90 seconds, perhaps stretching to 2 minutes in exceptional circumstances. Beyond this point, even if pressure is restored, the damage from oxygen deprivation and circulatory failure is fatal. It's a brutal, swift demise dominated not by explosion or freezing, but by asphyxiation and the unforgiving physics of pressure gradients. While a catastrophic helmet failure is thankfully rare due to meticulous design and checks, the inherent dangers of the space environment mean suit integrity remains a paramount concern during any extravehicular activity, or EVA, commonly known as a spacewalk. These excursions are essential for station maintenance, repairs, and scientific experiments, but they expose astronauts to direct risk. Micrometeoroid punctures, tears from sharp edges, or internal system malfunctions are all potential hazards. And sometimes the threat isn't the vacuum outside, but a failure within the suit itself, creating a different kind of life-threatening emergency. Consider the harrowing experience of European Space Agency astronaut Luca Parmitano on July 16, 2013. During his second-ever spacewalk outside the International Space Station, intended for routine tasks, something went terribly wrong. Early into the EVA, Parmitano reported an unusual sensation, water pooling at the back of his helmet. Mission Control initially suspected a leak from his built-in drink bag. Astronauts can sip water during long EVAs, but the amount of water seemed excessive and it continued to increase. Parmitano communicated the disturbing feeling. "It feels like a lot of water. It's in my eyes." The physics of microgravity dramatically worsened the situation. Water doesn't simply flow downwards. It clings, coalesces into blobs, and moves unpredictably with head movements. Soon the water crept over Parmitano's face, covering his eyes, filling his ears, and partially blocking his nose. His vision became severely impaired, like looking through a distorted aquarium. Communication became difficult as water filled his comms cap, muffling sound. Breathing grew increasingly labored as he tried to inhale without aspirating the water. Compounding the crisis, the ISS passed into Earth's shadow, plunging his surroundings into orbital night. Nearly blind in the darkness, disoriented, struggling to hear or speak clearly, and facing the terrifying prospect of drowning inside his own helmet, Parmitano had to rely solely on feeling his safety tether and his spatial memory to navigate the complex exterior of the station back towards the airlock. Recognizing the extreme danger, Mission Control made the swift decision to terminate the spacewalk immediately. Fellow spacewalker Chris Cassidy remained nearby, offering verbal guidance and assistance as Parmitano made the slow, tense journey back. Once safely inside the pressurized airlock, his helmet was removed. An alarming amount of water, estimated at nearly 1.5 liters, had accumulated inside. A subsequent investigation revealed the cause by contamination in the suit's sublimator, which caused water to back up into the ventilation loop and flood the helmet. Parmitano had been perilously close to asphyxiation, not by vacuum, but by water, trapped within his personal spacecraft. This incident became one of the most serious close calls in the history of spacewalking. It led to significant reviews of suit maintenance procedures, the implementation of helmet absorption pads, and even emergency snorkels inside the suit, all stark reminders that space remains hostile and survival depends on anticipating and mitigating every potential failure mode. But let's contemplate a different, perhaps even more existentially chilling scenario. Not a sudden, violent decompression, but a quiet, irreversible separation. Imagine a safety tether inexplicably failing during an EVA. A maneuvering unit malfunction sends an astronaut slowly, inexorably drifting away from the lights and safety of their space station or spacecraft. They are untethered, adrift in the infinite black. Rescue is physically impossible due to the distances and velocities involved. Their air supply is finite, ticking down. What passes through the mind in those final, isolated hours or minutes? Protected by the intact suit, they are shielded from the vacuum's immediate, brutal effects. They are utterly alone, watching their only haven shrink into the distance. As the oxygen level in the suit gradually depletes, their senses would dull, consciousness slowly fading. Perhaps the final fading view through the helmet visor would be the breathtaking, achingly beautiful panorama of Earth, a swirling blue, white and brown marble suspended in the profound darkness, continents and oceans impossibly clear. The sun, unfiltered by atmosphere, would be a piercingly bright disk. The stars, countless and unwavering, would surround them in silent majesty. The silence itself would be absolute, broken only by the sound of their own diminishing breaths. Maybe a final, poignant thought drifts through the hypoxic haze. So beautiful. No one will even know what happened out here. Just gone. A slow, lonely tumble into the eternal night. The vacuum of space is profoundly unforgiving, an environment fundamentally incompatible with unprotected human life. But the reality of succumbing to it is not the explosive, instantaneous annihilation often depicted in fiction. It is a rapid, silent, and ultimately physiological battle against oxygen deprivation and the overwhelming laws of pressure. Incidents like Jim LeBlanc's accidental vacuum exposure and Luca Parmitano's near drowning during his spacewalk serve as potent, terrifying reminders of the razor's edge upon which space exploration takes place. Incredible ingenuity of spacesuit design, the rigor of astronaut training, the importance of ground control expertise, and the critical human element of quick thinking and teamwork in averting disaster. Every successful spacewalk, every mission accomplished, represents a triumph of human capability, our ability to project a fragile bubble of life into the most hostile environment imaginable. The void remains deadly, an ever-present challenge, but for now, human ingenuity, technology, and an unyielding spirit of exploration continue to hold it at bay. What other mysteries or myths of space travel intrigue you? What should we explore next? Share your thoughts in the comments below. And if this journey into the realities of space survival captivated you, please consider liking this video and subscribing for more in-depth explorations of science, space, and the human drive to reach beyond our world. Thank you for watching.